Good evening and welcome to the demonstration presentation of Orca SR, a real-time traffic engineering framework leveraging similarity join. This is joint work done in our lab. Myself, G. Agustin, along with my teammates Suraj, Abol, Saravanan, Asade, Nansang, Govindas, Divesh Srivastava, and I would like to thank my colleague Balan for helping me to put together this demo. For the benefit of the audience, I would like to briefly go over the terminologies that we'll be using in our discussion. So one of the key questions that we ask ourselves is, given a partial information about the system, can we completely infer the state of the system? So to further explain, let us take the example of a subset of the authors that we have. Let us assume that each of them is communicating with the VLDB and Sigmund websites. Let us also assume that we also know the routes by which they are communicating to these websites. Routers are perfectly capable of learning the total volume of the traffic that they can handle. They also know how much traffic is there on each edges, but due to practical limitation, they cannot keep track of how much each person is sending to the destination and corresponding information. So thus we know actually aggregated information about the traffic volume on each edge, and also how much is the total routing metrics that we have. With this information, can we actually find out what is the source destination traffic volume? This is the question that we are asking ourselves. To further explain, let's take a small example in order to clarify the terminologies. There's the routing metrics. So there's a small example that you can see. There are two source and two destinations, S1 and S2, and D1 and D2. We can formulate the routing metrics as follows. Each of the row corresponds to an edge in the graph. Each of the column corresponds to a source destination pair. For S1, D1, E1, E3 are activated, and subsequently we have filled for each of the source destination pairs. Thus forms the matrix A, which is the routing matrix. Aggregate information on each edge is given by the B matrix. E1 has a total traffic of 50, E2 35, E3 30, and E4 55. So we also are given a prior value. We are trying to find out a value which is closer to the prior, but that is actually in the solution plane because the actual solution to the problem has infinite number of solutions. As you can see, we are trying to find the value which is closer to the prior. So the architecture of Orca, we are coming to the architecture of Orca. In this, we have the actual concept of Orca. The users will provide the parameters that will generate the network, which will be executed at the Orca server, which will be a Shiny application in our case. We compute the source destination traffics, and the results are sent back to the client browser where they are actually rendered for visual interaction to the user, and thus this completion of the cycle of Orca. We put together 4 scenarios where how to generate the user input, visualize the output, visualize the savings, interacting by subsetting. These are the scenarios that we are actually showing. This is the landing page of Orca SR. On the left-hand side pane, you can see that there are 5 scenarios. The user input selection and visualization, visualizing the input. Third, the final visualization of the source destination flows, followed by the interface subsetting. Lastly, thresholding techniques that we will use in our speed up. Basically, we will try to explore the first floor and we will try to see if we have time for the last one. There are 3 ways in which you can start doing this visualization. You can either generate a graph, or you can choose from an existing data set, or if the network engineer chooses, he can actually give his or her input in order to generate or simulate the graph. Because of the time limitation, we will try to focus only on the generation graph method. We will choose the Renai-Ados graph. We will choose a Pareto distribution of traffic. We will choose the type of the prior. We will choose the number of nodes as we like and a suitable threshold. Thus, we will ask it to generate a network. We can actually see that the network is being generated on the right-hand side. This will give you an idea about the topology of the network, which is very important for a network engineer in practice. When the graph is generated, the actual traffic flow is also generated, and we can actually start computing the source destination traffic flows, which is essentially what we'll be doing. We can actually interactively zoom in to see what are the artifacts of this particular graph by interacting with the graph to see what edges are connected to which of the nodes. Now we will go to the other scenario that we have. The second scenario that we have is visualizing the input, in which you can clearly see the exact reason of what we have explained previously of the routing matrix. The first line of the routing matrix corresponds to the number of edges and the number of source destination pairs respectively. The edge level traffic metrics that we will see in the bottom clearly gives the network engineer an idea about which are the most heavily used edges and which are the lightly loaded ones. A gravity pair represents the true template of the traffic that we are using in our actual computations. So during this time, actually the SD flows would have computed in the server, and we can really see, which is an interesting artifact of the solution. The users can, a network engineer can really see which are the important traffic that he should be like really looking at. He can filter through the traffic ranges. He can actually filter both based on the traffic IDs, whichever way he likes, and he can also search for different traffic IDs. You can also see the distribution of the traffic. Actually, you can see that the large number of traffic is contributed by very little number of the source destination pairs, but actually large number of source destination pair has a very few traffic which is there on the graph. Now we'll quickly move on to the subsetting feature that we have, in that we can actually choose a particular subsection region of the graph in order to particularly see what are the interesting aspects about this particular region. As you can see that I have chosen a couple of nodes. It has given me the corresponding source destination traffic, which is filtered, and I can know the aggregate information about them here. We also have a thresholding tab, which basically shows a network engineer how the individual, how we are achieving all this speed ups through thresholding. In the top blue regions represent the non-zero values that were computed. These are metrics in each of the values are computed before thresholding, and at the bottom we have shown them what are the effects of thresholding and some of the artifacts. With this, we will stop the demonstration. For more details, please refer to our work in the paper, and also we have given the link to the software where you can download from the GitHub. Thank you so much.